value for every time you spend watching our video. Kindly share, subscribe if you haven't, and tell others about it. Comment as well. Give ideas of how to add values, because my main reason of doing it is because of you. Thank you very much. Today we are discussing equation of motion and Newton's laws of motion. Why are we discussing equation of motion? These are the basic things, basic in physics, engineering. The mathematics of physics, engineering is really standing upon the equations of motion. That is the substance of engineering. Before we go into the equations per se, I would like us to discuss about some important quantities. One, we'll talk about velocity. Velocity means the rate of change of position. Rate of change of position in a specified direction. While we also refer to speed just as rate of change of position or distance. I want to let you know something. When we are talking in physics, in engineering, mainly when we mention speed, we are referring to velocity. We always put that direction in mind every time. Another thing we talk about is acceleration. Acceleration. Even as we look at velocity as change of rate of change of position, it can also change. So we also talk about acceleration. And acceleration is rate of change of velocity. Even at higher level, acceleration also change. So rate of change of acceleration, we call it jack, jolt, or lurch. We use this one in derivatives mainly, but later on, this is not in this place now. We are talking about acceleration. Now let's talk about another quantity called momentum. What do we call momentum? Momentum is the product of mass of a body with its velocity. So these are the main things that you must know before we proceed into this. We are talking about momentum, we are talking about acceleration and velocity. Another thing I want you to know is that at this stage we talk about particles. We look at most things we handle as if the dimension will not cause any problem in calculation. So when you look at it, particles are objects seen as particles are seen as objects which its dimension will not affect calculation. Else, at higher level, we talk about rigid bodies, and then we talk about system. Rigid body is collection of particles. System is particles or rigid bodies. Later on for that. Now, let's go into Newton's laws of motion. Isaac Newton was a philosopher, and he did a lot of studies. At the end of the day, he came out with 3 universal laws of motion. The first one says, every body continues in its state of rest or in motion in straight line. In motion in straight line with constant velocity, unless an external force or forces acts on it. What does this really say? It is telling us that when you place a body somewhere, it will not move, it will not fall, nothing will happen to it unless a force acts on it, or if it is moving in a specified direction. If you continue in that straight line, nothing will stop it, and it will not change direction, it will not change velocity. The velocity will not reduce, the velocity will not increase, it will continue with that constant motion, and unless a force acts on it. This now brings us to then define, to say what force does. Force. This is another quantity I want us to think of now. Force can be referred to as push or pull. That is, when you push something or you pull something. And what does force do? Force causes change of position. Another thing it does is it causes change of direction. What again? It can cause change in velocity. It can also cause something. Distortion of shapes, depending on how you apply the force. There are so many things force does. So, with this, it's sufficient for what we are learning for now. Now let's go to the second law of motion. It states that the rate of change of linear momentum is proportional to the applied force. and it goes, and this rate takes place in the direction of the applied force. You can see, now we have talked about momentum before, and this is, it's saying that rate of change is proportional to the applied force, and it goes on in the direction of the applied force. Now let's look at the equation you can bring out. We have said that momentum is equal to mass times velocity. Now if we now look at it, we can say momentum over time. Momentum over change in time is equal to, as in change in momentum, change in momentum is equal to, is proportional to force. Is proportional to force. Let initial momentum, initial velocity be equal to u, final velocity is equal to v, and then mass is equal to n in kg. Those are the units. Now, what is our change in momentum? Change in momentum is equal to mv minus mu, is equal to m into v minus u. You know, the mass is not changing since the body does not shatter. Now we now do something. F is proportional to m into v minus u over dt, and you will realize that v minus u over dt is equal to a. You will see that later on in equation of motion. I just try to bring this up first, and from the definition we have said that rate of change of velocity is acceleration. So we call this one ma. And in bringing the standard, they say that when mass equals to 1 kg, a acceleration is meters per second square. So if everything is 1, so f is proportional to 1 times 1, and we have k. So we are saying that if we have 1 kilogram, we have 1 meter per second square, f will be k. Yes, f will be equal to k. Sorry, I also change this one to k. So if we now in the scientific world, they now decided that let k be 1. So f is equal to ma, since k is now made 1. So that is about the second law, Newton's law of motion. The third law is very straightforward. Third law says action and reaction are equal and opposite. What does that mean? In this place, it is talking about force. It is talking mainly about force. So action, look at this. I am pushing the wall. The wall is also resisting me. My hand is pushing towards this place. The wall is pushing towards this place. If the force I am using to push the wall is greater than the wall can sustain, it will shatter the wall. So action and reaction at every point in time, these laws are observed in everything, in physics especially, in engineering, in mathematics. So action and reaction are equal and opposite. Let's look at this. This body is standing on the earth. Its weight is coming here. The earth is also applying this on its body. So this one is also W. Can you see? When it is resting on the earth. So we have W and W upward. So action and reaction are always equal and opposite. Let's look at another body now. A body. Somebody is pushing a cart. And this cart, it has a resistive force, let's say frictional force of 2 Newton. If somebody applies a force of 1.9 Newton, this frictional force will still be 1.9 Newton. The maximum frictional force you can apply, that's what I meant by that frictional force. But when the frictional force gets to 2 Newton, the pull here also becomes 2 Newton. So this one resists this one. There is tendency to move. Now let's increase this one. Let's say the mass of this one is 2 kg. Let's now increase this one to 3. Because this one cannot go beyond 2 Newton, there will be motion now. Are you getting it now? There will be motion. So the remaining force will be 3 minus 2, which is equal to 1 Newton. This 1 Newton will now come to the second law. Are you getting me now? When you get to the second law, you realize that F equals to ma. Therefore, 1 Newton will be equal to the mass 2 times A. A will be equal to 0.5 meters per second square. We have not yet gone into, I'm just using this one to explain the action and reaction. So when the body is moving, does not mean that it's not reacting. It means that the force is doing some other thing. If the balance of force is more than the one the body can resist, there is motion. That's what the third law is saying. Now to equations of motion. You can classify it to 3 or 4 equations of motion. But it's good for you to understand how it is derived, so that whenever you come across any exercise or question, you can resolve it with ease. Under this equation of motion, I would like us to also talk about graph of the motion. Graph makes it very easy for us to handle so many questions, just like Venn diagram for sets. So as I am explaining this, I will be giving you corresponding diagrams as well. Now, let's talk about a body with constant position from another place. Let's say this one is S from O. Let's say this one is S from O. And the position is not changing. The position is still the same as it is. If you want to draw the graph with time, this one is for constant position. Constant position. So what happens? You can say this is S. And this is T. You see that the position does not change all through. All through. The position is not changing. At least, so far, the question has made us to know. The position is not changing. So if we have constant position, the only thing we can get out of this is position time graph. Position time graph. And that is all. So in this place, V equals to 0. A equals to 0. So S is the only thing you can get, and that is the position at this place. That's all. Very straightforward. So now let's go to a body with constant velocity. constant velocity. When you have a constant velocity, look at it. V is constant. And you see, when this V is constant, you have said that distance or displacement, that's what I was saying. When you say distance in physics, you are talking about displacement. So, V, let's call this one S. So, S over T is equal to V. Straightforward. So, our S, you can say S is equal to VC. In this instance. In this instance. So, our graph is going to be something like this. C. V. Can you see? And this is velocity time graph. Velocity time graph. Please, these graphs are very important. Velocity time graph. The area under this velocity time graph, between the graph of velocity and time, this area A is equal to S for this. And when the velocity is constant, what happens? Velocity is not changing. It's not changing. So, what do you get? A is equal to 0. Acceleration is equal to 0. That is when you have constant velocity. Now let's look at when we have constant acceleration. Constant acceleration. Constant acceleration. Since our acceleration is constant, it means velocity is changing with time. Velocity is changing with time. So, sorry, please, before I go on. For this one, in this instance, sorry, S, you can plot the ST graph. ST graph. The ST graph, because it is like this, is going to be in this manner. As the time is increasing, the distance or displacement is also increasing. So this is it. And the rate, the gradient of this graph will be equal to V, constant V. So please note this. ST, I want you to get it very well. The S will be going straight forward. Thank you. Now, if our initial position is S1, initial position is S1, and it moves with constant velocity, our final position will be this, S2. So, S2 will be equal to S1 plus Vt when the velocity is constant. You can see, we are still talking about constant velocity. You get it now? So most of the time when we say, oh, there's a formula for S, the formula is about change of S, change of position. That is what it is. Change of position. So now, what is our change of position in this instance? S2 minus S1 is equal to Vt. That is it. Now let's go to constant acceleration. Constant acceleration. We know that A equals to V over T, or change in V over change in time. That is our A. So what happens to V? The graph will be like this. See? So since it is constant acceleration, we have straight line with slope, and the slope will be A. So this one will be V. And this is our A with time. A with time. It goes straight, it doesn't change. Can you see? So when you get this, A with time is constant. V with time changes. Now, let's assume that our initial velocity is U1. Let's see. Initial velocity is equal to U. So from this graph now, you can see we have U, and then it will now change with time. And you see T. This is for velocity. So our final velocity will be equal to U plus AT. That's our final velocity. This is our velocity time graph for constant acceleration. Constant acceleration. And please note the gradient here, gradient is equal to A. You can see. So U plus AT equals to V. The gradient equals to A. So you can see when we have a body moving with acceleration, constant acceleration, with initial velocity U, our final velocity after time t is going to be U plus AT. That is straightforward now. You can get it. Now, since we can get our velocity time graph, this one too. This one is for when initial velocity is equal to 0. You can see. But when the initial velocity has value, this is how we draw it. Now, let's take this as our model for calculating now. So, for our velocity time graph with constant acceleration, we'll take this as our normal all-time graph. So, we have something like this. U, V, and we have T. This is for T. This is V. Now, we know that V equals U plus AT. That is change in time, please. Change in time. Always put that into consideration. Change in time. Now, if you want to calculate the area under this graph here now, what does it give us? This shape is that of trapezium with parallel sides. Look at it. This place is U, this place is V, and this place is change in time. Or you can look at it like this. U, V, change in time. So it depends. Now look at the shape now. I have found it here now. So our area for trapezium is going to be half into sum of the parallel sides, U plus V times T. So let's use that T to represent our delta T is equal to area, which equals to total distance. Total distance. Now, we know that V equals to U plus AT. So, our formula for S, U plus AT into T is equal to X. So what do we have? We have half into 2U plus AT. Let me make it AT squared is equal to S. So S equals UT plus half AT squared. Straightforward. So this is the formula you use every time, mainly every time. Now, if U is 0, it's just going to be half AT squared. That's all. So then let's look at another situation. What is T? T, V equals U plus AT. So T is equal to V minus U over A. And if you look at this place, we have half U plus V. We have half U plus V into T is equal to this area. And T, we know that T is equal to V minus U over A. It's going to be half into U plus V into V minus U over A. You can see. So you can see. Does this equation look familiar? It's going to give us difference of two squares. So we are going to have S equals to V squared minus U squared over 2A. So V squared minus U squared equals 2AS. So our final velocity V squared will be equal to U squared plus 2AS. So when you want to solve any problem, when you want to solve any problem in physics, you will just know the equation to pick. We have this one. Even when you understand the derivation of the formula, you can easily handle any question. You just look at the parameters given, and from there you select, okay, this is in this equation, this is in that equation. So let's quickly summarize the equations. So we have V equals U plus AT. We have S equals UT plus half AT squared. We have V squared equals U squared plus 2AS. We also have this one, S equals to half V plus U into V minus U over A. So with all this, you can solve any problem under this. More so, when you know how to draw the graphs, sometimes this one might be lengthy, might be cumbersome. Just draw the graph and you get your answers. Another thing that came to my mind now is that sometimes we have questions where we are given velocity in kilometers per hour. But normally, the standard unit is meters per second. So we might need to convert this one to meter per second. Or sometimes we might be required to convert meters per second to kilometers per hour. How do you do that? If we have kilometers per hour, we want to convert to meters per second. So kilometer per hour will be equal to, how many meters make 1 kilometer? We have 1,000. How many seconds make 1 hour? We have 3,600. So you multiply the value of this one. Are you getting it? Okay, let me make it like this. With 10 over 36. So what am I saying? 8 kilometers per hour is equal to A times 10 over 36 meters per second. And if we want to convert from U meters per second, U meters per second to kilometers per hour, what do you do? How many kilometers are in meters. How many kilometers are in meters? We have 1 over 1000 kilometers divided by how many seconds are in hour? We have 1 over 3600. So what do we have now? We are going to have 1 over 1000 times 3600. So multiplied by u. So it's going to be u times 36 over 10 kilometers per hour. So you can see that's straightforward, please. Always know that. Now, I always advise that for you to enjoy physics, engineering, STEMs generally, it's good you have very good grasp of trigonometry and calculus. Just as an example, like when you have a body moving with constant acceleration and you want to find velocity, here you just do a dt is equal to v. So what happens here? You have when t equals to 0, from 0 to t. When t equals to 0, v equals to u. Velocity is u. So at time t, v will be equal to at plus constant. And how do you find the constant? When c is equal to 0, c is equal to u. So u equals to c. So that one gives us a plus at plus u, or u plus at. Can you see how straightforward it is? So if it is for distance 2, displacement, so s will be equal to vt. So for t, so you can see if v is constant, fine. But if v is not constant, look at what we have. So you change this one to u plus 80. So it's going to be t0 u plus 80, which will give us ut plus, okay, half a t squared plus c. Yes, that's how I do it. So what happens now? When t is equal to 0, when t equals to 0, if s is equal to s1, so what do we have now? We are going to have s equals to ut plus half at squared plus s1. So change in position, like I mentioned before, is going to be ut plus half at squared. Can't you see how interesting it is? No story, no long thing. It's just the normal integration. Now let's look at some examples. Now we have a question. It says a car moving with velocity of 54 kilometers per hour accelerates uniformly at the rate of 2 meters per second squared. Please calculate the distance traveled from the place the acceleration began to where the velocity reaches 72 kilometers per hour and the time taken to cover this distance. Now we know what our A is, 2 meters per second squared. Our U is 54 kilometers per hour. Please be always vigilant about the units. So how do we convert from kilometers per hour to meters per second? We have said it, times 10 over 36. 9 here, 6 here. So this is 15 meters per second. Please, I call this question from A-level physics. Ekon and Parker. Then our final velocity v is 72 kilometers per hour. So what do we have here? There we have it to be equal to 72 times 36 over 10. No, times 10 over 36. Sorry, 10 over 36. Please note, meters per second will always be lower than kilometers per hour. So here I have 20 meters per second. With this, I can go on. What does that say? It says calculate the distance traveled, that is change in position, total delta s, and we have an equation like this: v squared equals u squared minus 2as. So if you input this into this formula, you have 400 equals 225, plus 2s. 225 plus 2 times 2 times s. And so we have 75 over 4, which is equals to 4 in 15, 3, 13. So that's our change in s, 43.75. We are now asked another question. Where acceleration began to that where the velocity reaches now. And the time taken to cover this. The time taken, you can say v equals u plus 80. And what do we have now? We have 20 equals 15 plus we have 2. So we have 5 over 2, 2.5 seconds. So you can see, once you know the equation, just know which one to pick, and then you solve the problems. We can also try it with graph. How do you do that? It's going to be like this. This is our t, velocity. What is our u? 15. What is our v? Since it is constant, what is our v? It's 20. Can you see? And we are told that a is 2 meters per second. So we are told that the gradient is 2 meters per second squared. So what does that mean? If you want to find the gradient here, is delta v over delta t is equal to a. So our delta t now, you can get it. Delta t is equal to delta v over a. What is delta v? 20 minus 15. What is our a over 2? Which is equal to 2.5 meters per second squared. Can you see? The graph will give you, just know what you are looking for. Now the area is what you are looking for now. You have known that this place is 2.5. What is our area? Our area is going to be 15 plus 20 over 2 times 2.5. What does that give us? It's going to give us 35 times 2.5 over 2. And when you calculate, you are going to get the same answer, 43.75. So interesting. Physics is very, very interesting. You can see. So that's the answer. You can draw the graph, you can do it using the formulas. Now look at this question, which I would like you to try. A train starts from station P and accelerates uniformly for 120 seconds, reaching a speed of 48 kilometers per hour. It continues at this speed for 300 seconds and then is retarded uniformly for a further 180 seconds to come to rest at station Q Find one, the distance PQ in kilometers, average speed of the train, the acceleration in meters per second square, the time taken to cover half the distance.